네, 안녕하세요. 라이카 이우재 과장입니다. 소개 감사드립니다. 제 목소리 다 잘 들리시기를 희망을 합니다. 우선 올해는 이제 저희가 항상 그 세미나를 온라인으로 이제 진행해 왔었는데 부득이하게 이제 코로나 바이러스가 나오면서 온라인으로 오프라인 대신에 온라인으로 이제 진행하게 되었습니다. 그래서 어제에 이어서 오늘 두 번째 날인데 어제는 저희 역시 마찬가지로 라이카 소개를 이제 했었고, 라이카는 이제 많은 분들이 아시겠지만 170년 이상의 역사를 가지고 있는 회사입니다. 그리고 또 항상 그 기존에 그냥 이쁜 이미지 한 장 촬영하는 거 그런 거 말고도 혁신적인 기술을 항상 앞당겨가지고 우리가 만들어내고 있습니다. 그래서 라이카가 무엇을 만드는지를 보시면은 앞으로 어떠한 형태의 기술을 이용한 이미징이라든지 그런 실험을 대변하는 거를 볼 수가 있겠죠. 그래서 저희가 만드는 것, 저희가 항상 출시하는 것을 관심 있게 봐주시면 정말 좋을 것 같습니다. 그래서 어제에 이어서 오늘은 형광의 미경입니다. 어제는 이제 그 공초점 현미경에 관련해가지고 설명을 드렸었고, 오늘은 형광의 미경 중에서도 이제 썬더라고 하는 굉장히 빠르고 선명한 이미지를 만들어낼 수 있는 이런 장비에 대해서 소개를 좀 드리고, 여기에 이 장비가 가지고 있는 그런 신기술들에 대해서 이제 알고 계시면은 앞으로 실험하시는데 많은 도움이 될 것 같습니다. 우선 아시다시피 형광의 미경은 익사이테이션하고 에미션이 이제 중요하죠. 중요한 팩터 중 하나인데, 이런 형광물질들이 그냥 빛나는 게 아니고 어떠한 특정 파장대역을 받으면 우리는 에미션 빛을 보면서 그걸 이미징을 하고 있습니다. 공초점 현미경 같은 경우에는 핀홀이라는 구조가 있기 때문에 우리가 선명한 이미지를 촬영할 수가 있는데, 이 핀홀을 통과한 점들의 포인트 스캐닝을 해야 되는 점 때문에 아무래도 촬영할 때 시간이 일반 형광의 미경보다는 오래 걸리게 되죠. 위에서 아래로 삐 하는 소리와 함께 스캐닝을 하는 그런 작업이 필요합니다. 물론 좀 패스티스트한 그런 메서드들이 여러 가지가 이제 나왔지만은 그래도 실시간으로 이렇게 빨리 촬영하는 거가 중요하고, 핀으로 없애면 간단하게 우리가 스캐닝을 하지 않고 한 장을 바로 촬영할 수가 있는데, 시간을 세이브할 수 있는 것뿐만 아니라 우리가 3차원 그런 데이터를, 셀들을 데미지를 보호할 수 있습니다. 포토 톡시티시티라든지 블리칭으로부터 피할 수가 있죠. 그래서 빨리 촬영할 수 있는 것, 그리고 공초점 미경을 레이저를 사용하기 때문에 또 라이브 셀에 굉장히 이제 데미지를 많이 받게 되는데, 형광의 미경 같은 경우에는 이제 레이저를 사용하지 않음으로써 세포의 그 생존력도 높일 수가 있습니다. 하지만 핀홀이 없는 상태로 3차원 G스택을 촬영을 하게 되면 빨리 촬영하지만은 그냥 아웃 오브 포커스까지 같이 촬영이 되게 되는 거죠. 그래서 데이터로 촬영하기는 힘들기 때문에 우리가 선명한 이미지를 얻기 위해서 이 사이에 핀홀이라는 장치를 달고 핀포카 현미경 촬영을 했었는데, 이제 썬더라는 장비가 가지고 있는 거는 초점이 맞지 않지만 일단은 촬영을 하는 거예요. 그래서 옆에서 봤을 때 초점이 맞는 영역만 살리기 위해서 이 초점이 맞지 않는 영역, 이 영역들을 우리가 좀 제거를 하게 되는 거죠. 그래서 이런 제거하는 방법들은 굉장히 많은 방법들이 메서드가 있지만은 이런 메서드는 우리가 특허를 낸 거죠. 그래서 로우 데이터는 이렇게 생겼는데, 그리고 초점이 맞지 않았던 백그라운드를 제거를 하고 실질적인 리얼 데이터를 얻어내는 겁니다. 앞 슬라이드 잠깐 다시 보시면은 여기 보시면 뭐 PSF라든지 인포커스, 아웃 오브 포커스 이런 것도 있는데, 요거에 대해서 이제 그 제 다음에 이어서 발표하실 올리버 선생님께서 좀 더 디테일하게 설명해 주실 겁니다. 그래서 이 로우 데이터에서 백그라운드를 제거를 하는데, 이 기술들이 라이카에만 있느냐? 저희가 만들어낸 특허 기술이 있습니다. 이건 Computational Clearing 기술이라고 해서 이 기술은 라이카만 가지고 있는 것이고, 유사한 기술들이 다른 회사에도 많이 나오고 있을 수도 있는데, 라이카의 결정적으로 다른 거는 실시간으로 이걸 만들어낸다는 거예요. 일단 다 찍고 포스트 프로세싱을 하는 게 아니라 촬영을 하면서 곧바로 리얼타임을 만들어낸다는 거죠. 그래서 리얼타임을 만들어낸다는 게 라이카의 특징이라고 볼 수가 있습니다. 그래서 촬영을 하면은 G스택으로 이런 식으로 아주 빠르게 로우 데이터가 이런 컴퓨테이션을 클리어링 통한 바로 이런 선명한 데이터를 얻을 수가 있죠. 공초점 현미경과 달리 속도를 굉장히 빨리 얻을 수가 있고 블리칭도 피할 수가 있습니다. 이런 이미지는 G축뿐만 아니라 X, Y도 굉장히 빠르게 할 수 있는 하드웨어 퍼포먼스를 가지고 있습니다. 지금 96개를 촬영하고 한 포지션당 10개의 G 플랜을 3D 컬러에서 3분 30초 정도 걸렸다고 하는데 정리를 하면은 다음과 같은 표로 요약할 수가 있습니다. 그래서 한 포지션당 한 개 채널을 촬영하는데 40초가 걸리거든요. 근데 만약에 3D 컬러로 촬영하게 되면은 40초에다가 곱하기 3을 해서 120초 정도 걸릴 것 같지만 실제로는 6초밖에 차이가 나지 않게 됩니다. 실제로 형광 채널을 많이 늘린다고 해서 차이가 많이 나진 않는데 여기에도 기술이 있습니다. 하이스피드를 만들어내는 기술은 라이카 이제 만드는 이런 기술 때문에 굉장히 형광 체인지가 빠르게 이루어지기 때문에 그걸 실시간으로 할 수 있죠. 그래서 이런 기술에 의하면 형광 체인지가 왔다 갔다 하는 거가 빨라야 되는 칼슘 이미징이라든지 프레 이미징 이런 것들도 할 수 있고 라이브 셀 같은 데서 동적 그런 움직임이 빠른 그런 시료 촬영할 때도 모션 아티팩트를 줄이면서 촬영할 수가 있겠습니다. 그래서 이러한 시료들도 백그라운드 부분이고 혈관 부분인데 컴퓨테이셔널 클리어링을 통해서 원하는 이미지를 백그라운드 없앤 채로 촬영할 수가 있게 되는 것이죠. 그래서 오늘 이제 저에 이어서 설명드릴 거는 오늘 주제는 3D 이미징 enhanced by computational clearing. 그리고 썬더 이미징에는 굉장히 이제 한 개의 제품만 있는 게 아니고 복수의 다수의 제품이 있습니다. 그래서 각 제품들마다 특장점이 좀 있긴 있어요. 그래서 한번 올리버 선생님께서 말씀하시는 거 한번 잘 들어보시고 질문 있으시면은 편하게 질문 주셔도 되고 채팅창을 통해 가지고 해주셔도 되겠습니다.
Good morning. I hope you all can hear me nice. Welcome from Leica Wetzlar, Germany. It's a nice morning currently. If I look out of my window, no clouds available, so perfect day for this nice webinar. And yeah, annyeonghaseyo. Thanks for joining this webinar, and thanks for inviting me and giving me the chance to tell you something more about our new Thunder products. So the title of this presentation is Thunder Imager Family 3D Imaging Enhanced by Computational Clearing. And I would like to give you some more insights into the Thunder Imager family. I guess after this presentation, we will have also some time for questions and answers. So please put your questions in the chat and we will try to answer as soon as possible directly after the presentation. Thank you. So in the very first slide, I want to show you, you see the inherent problem of a typical wide field imaging system. And this is the blurry information. If you have samples in, you see a lot of blur in, which destroys all the image information. And that's why typically wide field imaging systems cannot be really used for thicker three-dimensional structures. And if you take a closer look on what a Thunder Imager system can deliver you, as you can see here, you see a much better contrast by disrupting the blur optodigitally from the images. I will come to that into a little bit more detail during the following slides. And luckily, also Ho-Che already did some presentation on that, what's happening. But before we come to all the details, I want to present you the Thunder Imager family members, which are consisting of different types of, let's say, microscope systems for different types of application. They're named, for example, as Thunder Imager Model Organism, a system based on a stereo microscope for model organisms like zebrafishes, C. elegans, or Drosophila larvae, for example. Then we also, the Thunder Imager family consists also of the Thunder Imager tissue and 3D tissue based on an upright microscope for mainly thicker tissue sections and automatically scanning of these sections and getting nice image information out of that. Then we have also the bigger family members, which are consisting of the inverted family based on the DMR8, which is consisting of the Thunder Imager 3D cell culture, 3D live cell, and 3D assay. What that means, I will come to that a little bit later. And then we have also a new member in the Imager family since we presented this to the market. And this is the Thunder Imager EM Cryoclam for combining and combining wide field fluorescence microscopy with electron microscopy in a correlative manner. Thunder imagers are a new class of instruments which deliver benchmark application performance, especially in the fields of 3D cell culture, model organisms, and tissue sections. As you can see here in this image, there's already a big tile scan done in wide field, so in standard wide field, and on the fly, we get also this nice contrast-rich blur-free images. So if I toggle back and forth, you can see directly the difference between the Thunder images. Also in this image, you can see that during the acquisition, we also get the Thunder image information available. More information comes later. So before we go on, I want to step a little bit further into the Thunder technology. So the core basis and the core technology of all the different Thunder images I have shown you already. And the core technology is the so-called instant computational clearing. As I said, it's a core technology of Thunder, and it's not just a basic background subtraction. It's let's say a feature-based optodigital method which reduces the background and the inherent blur of your wide field samples. How does that work? First of all, we only need a single image. So there's no need to acquire several numbers of image. It works already on a single plane. So no need to acquire a set stack or to, for example, put in a grid projection to acquire some more data and then to calculate another image. Here we just need a single image coming from a camera system, which is based on the Thunder Imager. If we have a wide field image, which looks, for example, like that, we have two informations actually inside, which is on one hand, the blur itself, which comes from regions above or below the focal plane. And then we have the in-focus structures. So the Thunder algorithm divides these two different structures by detecting the in-focus structures by the so-called feature length. It's a, let's say, it's a defined value which the system knows out from the optical components and the wavelengths you are using, and it's automatically used during the imaging so that it's able to detect the in-focus structures which have a much more narrow, let's say, PSF, or even a much more narrow feature size, so to say, compared to structures which are out of focus, which are much more broader and more homogeneous in staining. So that means after subtracting then this information, you get an image like that. So to look on a different sample, we can see here just a crop of some nuclei stainings here on a DAPI staining where you see a lot of background. And after applying the instant computational clearing from Thunder, you get a nice black background, and also the features and the signal to background is much better visible. Here you see the line scan, which has, let's say, a sum of all the information in this image, which is the information of the feature plus all the background around. And after applying Thunder Instant Computational Clearing, or ICC, which is the abbreviation of that, we subtract, so to say, feature-based the background around the features and then get a much better contrast in the image. So why do we do that? Well, you have to know that on a wide field image, you will typically get inhomogeneous illumination, or you get inhomogeneous background around the sample. And if you just, for example, in this example, these are just beads put on a slide, which has another fluorescent staining in the background, which is rather inhomogeneous. And if you took some images of beads where you have a high background available, you get a higher signal because it sums up with the signal. If you if you take an image where the background is lower, you get a lower signal. So you cannot compare the image information you directly see in the raw image in a raw wide field image. This you have to know. And with Thunder Instant Computational Clearing, as we subtract feature-based, so based on the features itself, the background around the structure, you now are able to really quantify the images. So a qualitative manner is already can be done on standard wide field images, but quantifiable image data you only get after subtracting the background. This is very important to know. On top on the Thunder Instant Computational Clearing, we have other methods. One of it is called small volume computational clearing. And this method combines the feature-based background subtraction with an additional deconvolution algorithm, and therefore enhances the signal to noise even. So it gives you a much better contrast and shows you much better details in the images. And we have two algorithms working here. One is the cell, which is called then the small volume computational clearing, dedicated to very thin specimen. And then we have also the large volume computational clearing, which is then a combination of instant computational clearing plus a Leica-based deconvolution algorithm you might know from the lightning approach, from the lightning microscopes based on an SP8, for example. And this deconvolution is then also adapted to the large volume computational clearing, which gives you a higher detail on thicker samples. Thunder itself is fully integrated in the Lsx workflow. So as you see in the very last part of this presentation, we have then a little live demo. You can activate it on the fly by just checking the different icons here. So instant computational clearing, small volume or large volume computational clearing, and then it's directly adapted to the sample. Or as we always keep the raw data, so we never throw away any raw data, you also can use the post-acquisition methods, as you can see it here, and apply it again to your still available raw data and play around with some feature settings and so on to get an even better image quality. Now let's come to some more detail about the Thunder Imagers itself, so the instrument. So we will start with the Thunder Imager model organism based on a stereo microscope. With the help of this stereo microscope, which is our M205 series, it has several nice features. One of it is the fusion optics, where I will show you later on some images on that. And also it is combined with a high quantum efficiency camera. And to be able to fulfill the needs of the model organism imaging with high resolution, we also offer dedicated objectives, like, for example, the 2x Plan Apo objectives, which has a correction ring for correcting the spherical aberrations if you have to image into water itself. So if you have water embedded samples like zebrafishes or something like that, this lens can correct for the aberrations if you image into the water. Further on, we have the so-called fluocombi mode, which diverts the stereo microscope into a macroscopic imager, which is then very nice if you combine it with this 5x 0.5 plan apochromatic corrected objectives. And on top, for automatic multiple stage experiments, we have a fast stage available. So every stereo microscope, especially here the Thunder Imagers, come with the so-called triple beam technology, which divides the excitation pathway from the observation pathway. So with this, as we have three different pathways for observation and for excitation, you get much less reflection, and therefore already during the acquisition less background, and therefore you enhance also the signal to noise in your images. The fusion optics is very important to mention, because here you see a look into the microscope optics, which where you see here the two beam paths of the microscope for observation, and this is the excitation beam path. And you see for the beam path for observation that we have two different so-called apertures, so different sizes. So here we get much more light through than here, which means here we have a higher resolution and here we have a higher depth of view. If you look through the eyepieces with your own eyes, and then your brain mixes these two images up, and then the brain is combining the high resolution image with the high depth of field. If you use a camera, of course, then the camera is using this pathway here, where you have the highest resolution available, because for the camera imaging you use the highest resolution available and the most possible light you can get. The next imager I want to mention is the Thunder Imager 3D Tissue and Tissue, which are based on an upright microscope, which is, for example, on basis of the Tissue Imager, an upright microscope which has a motorized stage, a fully automated contrasting method, selecting method, and a dedicated fluorescence camera, which is also a color camera, which is also possible to use for fluorescence imaging. And this imager is suitable for multicolor 2D tissue imaging. It doesn't have a set drive to do a 3D imaging. So let's say it's a starting or let's say a basis configuration of an upright Thunder Imager. The high-end configuration of the Thunder Imager in the upright world is the 3D Tissue Imager, which is suitable for multicolor 3D tissue imaging. So because it has a fully automated upright microscope as a basis and comes with a full equipped imaging software. And therefore, as it is possible to switch also objectives and different magnifications with the motorized stage and the motorized Z drive and automated contrasting method. It is perfect for automated tissue section imaging and, for example, TMA, so tissue microarray workflows in combination with Thunder. Then, based on the inverted line, we have the Thunder Imager cell culture, for example, and the inverted microscopes are typically, if you use a standard wide field microscope, you cannot really reach the now upcoming and trendy more applications. Stepping back from 2D cell cultures basically up to the more 3D world, starting from basic 3D cell cultures to spheroids up to even organoid imaging. With standard wide field imaging, because of the inherent blur, you cannot really reach this with a decent image quality. And the Thunder images enable you as a user to use this instrument to further go on with this imaging capabilities. So the Thunder Imager is also divided into three different, let's say, ranges. So the starting range is the 3D assay imager, which comes with a rather sensitive stage, which is a scanning stage. And then we have a passively cooled CMOS camera here for fluorescence imaging, and also the possibility to put on the fast external filter wheels, which shows already. The next step is then an upgraded version of the 3D assay, which is called the 3D cell culture, which comes with our quantum stage, where I come to that in the next few slides. On all the benefits, it comes with an adaptive focus system and a high sensitive, actively cooled camera. Then on top of that, for those who want to really go into the live cell imaging, we have an updated version of the imager, which comes with a complete enclosing of the microscope to enable our users for really 3D live cell imaging over even days, and screening of multiple blades and growing of spheroids automatically in this imager. So the technology behind that is also that we want to keep the sensitivity as high as possible with these Thunder Imager configurations. One crucial part in this configuration is the real-time controller, which controls every single component which is part of the microscope in a sequence. So let's say you don't have the real-time controller inside, then illumination, so for example, switching on and off of the lamp plus the acquisition which is controlled by the camera, is not really synchronized. So that might be that your illumination takes longer than the real exposure time the camera needs. So therefore you put more light on, and therefore it might happen that the light stress is so bad that you introduce photo damage and bleaching. So with the real-time controller, you synchronize illumination up to the exposure and therefore minimize the light exposure to the sample and therefore minimize photo damage and bleaching, and therefore enables you to longer image your sample. This comes in line with the new LED light sources, which also come with this imager. So we have a set of different light sources where you can choose from. All of the different light sources are based on LED with a fast shutter. So they shutter below 1 millisecond, as typically LEDs will shutter, and you can have up to 8 different LED lines, which help you to combine different fluorophores into one experiment in a high-speed manner. In terms of sensitivity, it's also important to talk about the optics. Optics directly collect the images itself, and therefore they collect the photons out from the sample. And therefore it is very important to think about high numerical aperture objectives which are dedicated to lifestyle imaging. And one of it is water immersion objectives. Water immersion is one of the crucial methods you should use for lifestyle imaging, because you have water embedded sample, and if you would use a non-water immersion objective, you might introduce artifacts by introducing spherical aberrations the deeper you go into the sample. That's why we have, for long-term imaging, an additional water immersion dispenser, which adds automatically water to the water immersion, because during lifestyle imaging, you are under a certain temperature, and therefore the water might evaporate. And therefore, we have this water immersion microdispenser for automatically applying water. One further advantage to use water immersion compared to, for example, dry immersion, is that with the higher NA, you have a much better sensitivity of all the system, but still maintaining a decent travel range, which you need to focus into, for example, 3D cell cultures, and which are grown, for example, in hydrogel or some other polymer embedding media. So therefore, now you get both a high sensitivity, high NA for high resolution, and also the possibility to focus deep into the sample. Then over long-term imaging, you need to keep the focus stable. And in our case, our adaptive focus control, or AFC, is the powerful solution for maintaining the focus. So it's actually using an additional LED illumination by 850 nanometers, so very long wavelengths to not disturb or anything within the sample, and therefore maintaining the focus automatically during the image information without adding additional light for fluorescence, for example, onto the sample. Then for being fast, one crucial step is having also a perfect stage. And with the Thunder Imager 3D live cell and 3D cell culture, you can also have the fully triggered and integrated quantum stage. It's a fast, fully synchronized stage, which is synchronized with the imaging, with the illumination, so that you get the fastest speed available with a high precision. now let's come to some of the applications of these Thunder imagers, and let's have some examples what has been done already by some of our customers here. And we will start with one of the images a customer here close by in Wetzlar, by the way, in Gießen, also did with a smooth muscle around blood vessels here. So you see here on the left side, you see always the standard images you get out from the wide field microscope. And then you see here the Thunder imager, where you see already a much higher signal to background in this image, which gives you more details available. Then here's one example from the model organism imager with a beating zebrafish heart on a live zebrafish. And here, this is the same zebrafish scanned in 3D, one time in wide field, and then we also showed directly here the Thunder images. Then here a side-by-side comparison of a cortical spheroid, also imaged with the Thunder imager model organism in a multi-well plate. As you can see here, because of the thickness of this sample, you see a lot of blur in, whereas in the Thunder imager, this blur is gone, and therefore you see much more finer details in the center, especially here in the red signal range. Then a side-by-side comparison of a C. elegans in wide field and in Thunder. Then this is a very nice image of a sea anemone polyp, also acquired with the Thunder imager model organism. Then we have here some mouse heart neurons of, as you can see here, a more than 300 micron thick slice, so to say, where you can see also finer details even in the lower planes by applying Thunder automatically to this image. This is an example from the Thunder imager 3D tissue, for example, where the customer was using a tissue slice, which is 120 micron thick, stained with GFP stained neurons here, and also anti-GFAP, which is the red signal, which is some proteins of some astrocytes. As you can see, in the pure wide field image, all of the information is already lost. But applying Thunder, you even can see the processes and the finer processes of the neurons, which are here then available. Then a side-by-side comparison of a mouse lung, again between the two different images. Some neuromuscular junctions. As you nicely can see, they're nice. The structures are much better available in the right image side because the contrast is much more visible here. So, and then you see also the effect on how the different methods can help you to even enhance the image quality. If you see here on the left side raw data, then instantaneously you get the instant computational clearing image, which enhances already very much the contrast. But then if you use, instead of ICC, the large volume computational clearing, which applies an additional deconvolution step to that, you see even more finer details of the sample. Okay, so now let's come to some advantages you have in case of these Thunder images. Well, besides having a full equipped microscopic imager, you also have to see how everything is integrated. Well, you reduce the complexity by integrating this Thunder imager technology directly in the standard imager workflow. So with the help of that, we can have a very user-friendly system where it's easy to learn and also for everybody easy to step into creating also complex experiments. Then with the help of the real-time controller, we are also fast, which is needed for if you have high dynamic experiments, but also if you want to upscale your experiments, if you want to do different number of experiments in the same time. Then, as I already mentioned, you increase the data quality by having besides nice images, you have also now already directly out of the box quantifiable images. Then, and this I will come also in this section to that, you with the Thunder images and the help of the software tools, we allow transfer the images across imaging platforms. So as I already said, you get nice quality images for quantitative analysis by directly applying instant computational clearing to the image, where you see already nicer details available. Or if you directly apply large volume computational clearing to that, you see much more finer details, which helps you to create or to make structures available for automated image analysis, where you can use the integrated analysis workflow we have in the software, which guides you through all the setup of an automatic analysis. And here in this case, our customer was even using the wide field image, which is the blur of the cell here, to create the outer area of the cell. And because he was interested in counting the spots per cell without using another counter staining of the pure cell. So he just uses the intrinsic staining of these little vesicles here and uses the wide field blur even to get an idea what the size of the cell is and the volume of the cell, and then is using the thundered image with the little dots in here to automatically count them per cell. So another example we have was quantification of different cell populations. In this case, we have, for example, a DAPI counter staining, and we also see nuclei which show different GFP expression levels, and we have additional 2 markers. And these 2 markers are interesting only at a cell which has a certain GFP expression level. So we have two things we need to mention here. One, we need to know the GFP expression level, and then if there is marker 1 in or marker 2 or both. Okay, this was the question here. So what we then use is we use a big overview of the cells in different colors, using then Thunder on top to get a decent quantifiable image data set. And then we use the automatic workflow of our analysis tool to detect, first of all of the cells, then to get the information of only the cells of the detected cells which have the certain GFP expression level. And then we took the different marker settings, and then we get directly out of a total number of 4,513 cells, we get 213 cells with marker 1 with the right GFP expression level, and 451 of the other GFP of the other marker and with the right GFP expression level. So this is done with the integrated analysis which comes with every Thunder imager, and the imaging itself is done with the help of our Lsx Navigator, which gives you the possibility to choose from different sample holders like multi-well slices or multi-well plates. Something like that. And the Lsx Navigator, our software tool, helps you to automate all of these images. For example, getting an automatic overview scan of the whole slide, then Thunder it, and then look into the details and, for example, count the number of cells, and then count also the cells which show a certain expression level. Another example is here a growing Arabidopsis root, where you see during 8-hour live cell imaging, this root is nicely and happily growing around. And then after a certain while, you see how the tips are growing out from the Arabidopsis root here. So as I already mentioned, the Thunder images enables the users for imaging across platforms. So we have the wide field images, which here with Thunder we enable you to enhance the contrast by using instant computational clearing or large volume computational clearing, and step into the world where you typically only can use a confocal microscope. We do not really reach it completely, but we fill the gap between the confocal world and the wide field world, so to say. Okay, here I want to present you one example a customer did with both worlds, so to say. He uses a Thunder Imager to pre-screen a mouse momentum here. And this mouse momentum shows different features, like, for example, this FALC cells or FALC cells. And these FALC cells are typically presented here in this very bright spots over there. So after pre-screening very nicely and very fast with the wide field Thunder Imager, they can use, of course, Thunder to detect the areas of interest where the FLLC cells are available. So now they can feed this information into our Lsx Navigator, and with the help of an alignment tool, you can use the Thunder overview, can go to another system like the SP8 confocal or the Stellaris confocal, can feed in this Thunder overview, and you can put your slide on, and you can reuse the same area, like here, with the Thunder overview, and you now can go with the SP8 confocal to this area and get a nice overview scan and a nice high detailed scan in confocal mode, and even combine it with the Lightning higher resolution mode of that, and to see very finer details. So this is a nice example on how to combine and correlative step into this world. The last member of the Thunder Imagers is the Cryoclam Imager. So it consists of a fixed stage microscope with a dedicated stage and a dedicated tool for moving already frozen cryo sections to the stage and maintain the temperatures under liquid nitrogen under the microscope to pre-screen the images which you want to use later on an electron microscope. So typically in cryo electron microscopy, you have images like that. So for example, and so this is a wide field image where you see where the grid is broken like that, which you don't want to use. And here you have some crystalline ice contamination in there, which you don't want to use. But you want to detect, first of all, which are the areas you want to use for EM to save time. And further on, if there are cells of interest on which you then also want to use. So if you then use this image information, you can define the coordinates which are interesting for electron microscopy. You then can transfer it via a simple holder to the scanning electron microscope, and you get the same correlative image to that. Of course, if you have thicker samples like that and you want to see some finer details, the Thunder Imager is also combinable with that, so that you can automate and fasten the imaging workflow of these Cryoclam information. And then later on, you can imagine that if you do it with, of course, with a lot of work and with the different stainings and also different imaging methods, you can get images like that, where you even see molecular structures in cell membranes by using, of course, electron microscopy and step into a more high resolution world. So the Thunder Imager EM Cryoclam consists of different nice features, which is the dedicated objectives, which is developed for working under cryo observations. So where you have liquid nitrogen, and the objective is dipping into the liquid nitrogen and gives you a very great image information and image quality. Then we have the so-called cryo stage, which is on the microscope, where it is filled with liquid nitrogen via here. And it offers, let's say, a door where you can transfer the frozen sample directly to the microscope without releasing or let's say, dropping or dropping the temperature from the sample. And this is done by the so-called transfer shuttle, where again liquid nitrogen is in, and where you can prepare your sample itself, and then it's transferred via this tube, so to say, directly into the liquid nitrogen under the microscope. And therefore, your frozen samples on the cartridges here, for example, are not heating up, so to say. So, last but not least, a summary of the different Thunder Imager family. We have the Thunder Imager model organism based on a stereo microscope, Thunder Imager tissue based on an upright microscope, and Thunder Imager 3D cell culture, live cell, or 3D assay based on the inverted range, and the Thunder Imager EM Cryoclam. So with that, I would like to directly step on with giving you a short live demonstration on what's going on. So we are here currently on the microscope, and what you see here is this little square where I activated now the image, and by just moving the mouse wheel, I can zoom in and zoom out to my image area. But as I have here a slide in, I just select here my direct slide so that I know, okay, this is the position where I am. This is a representation of the microscope slide, and I can double click around to search for my sample. But the much easier way is to use the Spyro Scan, which I'm now clicking on. And with the help of the Spyro Scan, I'm automatically imaging a spiral around the starting point, and therefore it helps me to get first of all a nice overview of my sample, to have an idea where I can navigate around. And like in Google Maps, for example, you can use the mouse wheel and you can nicely navigate throughout a sample, as you can see here. And let's have a look on some of the structures here. First of all, I need to check my imaging settings. Okay, so here I have three channels already activated. That means we have 3 different stainings in. Then I switch to the 40x objective to get a better resolution. And then I use the mark tool here to mark different positions here, like this glomeruli in this kidney section. So these are now 2 different positions. And by the way, if I, for example, change objectives, you get a live update of the area you are imaging. So these are 2 different positions in the different sample to keep it simple. And I'm using the 40x objective. And I also activate a set stack because we have also a 3-dimensional structure. Then I move to the first position, activate live, select the channel which I want to use. And then I just define, first of all, the start and end position of my set stack. This is very, very fastly done. So end, okay. So then I select the system optimized position, which calculates me 26 images are needed for this volume. And then I just activate Thunder, nothing else. So it's just a single click. And after I start the images, you directly can see that it acquires the data in wide field, but I also get direct access to the thundered data. So this is the wide field data, first of all. And you can see I also get the thunder data directly available, right? So this is, for example, the green channel alone. And then let's check the other one. Here we have also everything imaged. Then we go back to the first one and let's compare it to the wide field. So during the acquisition, we get already the Thunder Imager data available, and you directly can see how huge this effect will be. So the blur is much less compared to the wide field data, whereas here you see much more data inside, or at least, let's say, more contrast. Okay, wide field. And let's go out. Let's go back to our overview. And now let's use our polygon drawing tool tool and draw an area of interest in here. So as you can see, inside this area, the navigator automatically calculates me the minimum number of images needed to cover this area with the wide, with the images itself, with the image area. Then I define another set stack here. And just for sake of time, I just select only 11 images because, yeah, now it takes a little bit more time, of course, but you will see how fast it works. So I'm only switching the illumination light, and you see how fast the different channels per stack step in, right? So we already did 3 steps. Now comes the 4th, and so on, of this whole volume. And as you can see, you also can see live how the Thunder images become available. So you do not have to wait until all the images have been acquired. During the acquisition, you directly can see the effect on Thunder. So it's just a part of the workflow, fully integrated. You don't need to think about decent settings on Thunder. So after that, we just can merge the sample. You can also set the navigator that it automatically merges after that. And now let's go also to the wide field one. So here you see the comparison merged versus unmerged. And then the wide field we also merge together. So you see, this is, by the way, already a stack of 3.3 gigabytes. So it's some data which needs to be aligned, but this is very fast. And then let's go to our 3D viewer. We can have a nice 3-dimensional overview of the multicolor stitched set stack now. A wide field on the left, Thunder on the right. Thunder was instantaneously available directly after the imaging. So now with the red channel, now let's compare the green channel. There you can nicely see the structures available in the glomeruli. That's a little bit adapted. So, okay. So you see much better contrast there. And yeah. Okay. So now I told you that we always get the wide field raw data available. So we don't throw it away. So that means we can reuse it. For example, for applying the large volume computational clearing to that. So here I click the zebrafish icon, use the wide field data, and set it to automatically calculate the imaging data. And now it calculates also live. You can see how the images were created. And then after, let's say, when is it finished? Now, after 23 seconds, we already calculated a full image data set of nearly 800 megabytes. And now let's have a directly side-by-side comparison using the multi-viewer tool here in the Lsx software. So on the upper row, we have the wide field image. Then on the second image, now on the right, we have the instant computational clearing image. And then on third, we have the large volume computational clearing image. So you see already, let's say 80% of the work is done by applying the core technology Thunder to the images automatically during the imaging workflow. But as you can see with the large volume computational clearing, especially when I switch to the red channel only, you see more details become available. Yeah, I think this is a nice comparison of the image data. And the important thing is that we are not only using this adaptive approach on detecting features to subtract the background, we can also apply a decent and a dedicated deconvolution to these sets of images. So with that, I want to go back to my presentation and show you the last slide. Please first of all, thank you for your attention. And you can visit us under www.leica-microsystems.com Thunder to get some more information on the Thunder images. And thank you very much for your attention. 감사합니다. Thank you.